arm forward. So in a way, my brain is smart enough to understand that in anticipation of this movement, something has to be done with the activation of leg and trunk muscles to make sure that the posture is preserved. So these are called anticipatory postural adjustment. But I am going to introduce one more notion, which is probably less known, that when you prepare to perform a quick action, synergies stabilizing the variable that you are going to change in this action are going to be attenuated, decreased in advance. I'm going to call it anticipatory synergy adjustments, and I'm going to introduce them very, very soon. But before doing that, I want to talk a little bit about anticipatory postural adjustment, because I think there is a lot of confusion about them. One of the confusion is that people call postural preparation to stepping also anticipatory postural adjustment. And I think this is very, very wrong. It's a completely different animal. And I'm going to tell you why. So here we have two types of postural adjustments. One of them is an adjustment to an expected perturbation. And that's anticipatory postural adjustment. Its purpose is to generate forces and moments to counteract the expected perturbation. It's usually seen about 100 milliseconds before the perturbation comes, or before the action is initiated by the person. And then there is another type. These are postural adjustments to action when there is no perturbation at all, like stepping or something like that. They adjust posture to make the planned action possible. In a way, they are mechanically necessary. Anticipatory postural adjustments are not mechanically necessary. You can do this movement without anticipatory postural adjustment. You are not going to fall down, because the posture is pretty well protected. There will be other later mechanisms that allow you to balance. They are seen way, way earlier, 400 milliseconds to a second prior to the action, and they are early postural adjustments, I'm going to call them. So, a typical example of anticipatory postural adjustment: lift your arms quickly, as I just showed you, or drop a load, or catch a load. They depend on perturbation, obviously. They depend on action magnitude, which is a little bit less trivial, but they do. Postural stability and time pressure. For example, if you ask a person to do a movement as quickly as possible to a beep, anticipatory postural adjustment will disappear. They will move to action initiation. They will not be there. If you ask a person to make a step as quickly as possible to the beep, early postural adjustment will be there. Simply because you cannot make a step otherwise. You have to change your posture to make a step. Okay, so they're rather stereotypical, obligatory, and there are minor changes under time pressure. And I'm going to show you an example. So this is an experiment, or a piece of an experiment that we ran with one of my colleagues, Alex Aruin, in the University of Illinois at Chicago. So the right picture illustrates the main experiment. He has a very nice device. It's a pendulum attached to the ceiling, and it swings and it hits the person on the shoulders. So you're standing like that, doing nothing, and you watch this pendulum coming and hitting you. You cannot do anything, but it's not very strong, fortunately, so nobody falls down, and it's padded, so it's relatively soft impact. And people show very nice anticipatory postural adjustment in preparation to that hit. But they also show nice early postural adjustments. Now, take a look at this picture. Now, it shows EMGs of a bunch of muscles in that experiment. On the top, it's soleus, lateral gastrocnemius, erector spina, lumbar portion, and on the bottom, tibialis anterior, rectus femoris, and shifts of the center of pressure. You can see the arrows show on the top that the activity of some of the muscles starts to change at least half a second before the impact. This is not an anticipatory postural adjustment, and it's not intentional. People just getting ready. So people adjust their posture a little bit to make sure that the hit is not as perturbing for the posture, without realizing what they're doing, because they're explicitly instructed not to do anything like that. But everybody does it. And then, particularly at the tibialis anterior, you can see a real anticipatory postural adjustment. So a burst of muscle activation about 100 milliseconds before the impact. Now, if you accurately take a look at soleus and lateral gastrocnemius, you will also see about 100 milliseconds prior to the impact, which is shown by the dashed line, a very abrupt drop in their activation. They're nearly silent in those two muscles. So these are anticipatory postural adjustments. So in one experiment, you can see both following each other. And they show different modulation with task and other things. Okay. Preparation to making a step. Okay, let me skip that and show you that, okay. This picture shows, we asked our subjects to make a step in a natural way, quickly, and as quickly as possible to the beep. And this shows some different muscle activation patterns. But the interesting picture is that, which we did not, at the time we recorded it, we didn't really realize what we are up to. Now, this picture shows the index of synergy, stabilizing center of pressure trajectory in the anterior-posterior direction, done in the same way as before I described. So it's a multi-muscle analysis. Muscle modes are defined, and in the space of muscle modes, covariation is quantified with respect to the trajectory of the center of pressure. And these are three different conditions. Now, in the swing leg, you can see that the last two clusters of columns are smaller than the previous ones. So, about 1 to 200 milliseconds prior to the initiation of stepping, somehow the synergies that used to stabilize center of pressure, synergies within that half of the body, started to be phased away. At first we thought, well, it's a smart idea because when you lose contact with the ground, when you initiate the step, now muscles of this leg cannot do much to stabilize center of pressure because you don't have contact with the ground. So it makes sense to phase out synergies. So we had this kind of hand-waving interpretation of this result. Then we realized later that that was probably the first occasion when we saw anticipatory synergy adjustments. So before introducing them, let me show you this picture, two pictures, and ask the question, what do you think the difference is between these two pictures? Don't tell me that one is a bird and the other is a plane, I know. And don't tell me that one is made of metal and the other of meat and feathers, I also know that. But let's imagine that the bird is soaring, so not flapping its wings. And so these are two objects that are soaring in space, flying in space. Now, what's the big difference, striking difference in the design? What's the difference?
So for the bird, the wings are more, well, have another curve, right?
Well, this is minor. I mean something major. What does the plane have and the bird doesn't? Don't say engines because, well, the engines in the bird are not visible. So what else? The tail fin, the vertical tail fin. All planes have this vertical thing at the tail. No bird has it. Why? Well, one has to think, why do planes have the tail fin? Well, it is there to ensure stability of the plane, so that the pilot doesn't have to think too much while flying a passenger plane about stability of the plane. Okay? Why don't birds have it? I actually have a hypothesis for paleontologists, if there are paleontologists in the audience, that early in the evolution there were birds with a vertical tail fin, they were all eaten quickly. Because if you are stable, you are not maneuverable. There is a trade-off. If you are very stable in your performance, you cannot change quickly. Passenger planes don't have to change quickly, don't have to be maneuverable, because that's not what they're designed for. By the way, fighter planes have much smaller tail fin, because it's probably optimal to ensure both stability and maneuverability. So the birds don't have tail fins, vertical tail fins, because for birds maneuverability is much more important than stability in the air, I guess, because otherwise they're eaten too quickly. So maybe stability is overvalued, and this...
I'm sorry, if the bird just doesn't fly but soars, then it doesn't have a steep respect to the air. So
Yeah.
it just doesn't mean any tail because there is no point. On the other hand, the plane, well, it goes with high speed, and so the tail is useful. And for the bird, it just useless if it soars.
Yes, but if it starts flapping wings, the vertical tail fin also would help in general for stability purposes.
Flapping wings that become so much complicated that other features of the bird just make.
Well, okay, so yes, the example is not perfect because when the bird soars, correct, it soars with the air. Although I would say that sometimes it starts to soar not exactly with the airflow and it stops to soar also not exactly, because it usually flaps wings, then it starts to soar, then it loses speed, it flaps a little bit again, so it doesn't soar all the time with the wind. It drags a little bit. Okay, this is only an illustration. So. Here is the experiment where we, for the first time, found this interesting phenomenon, to us interesting, which we call anticipatory synergy adjustments. Here is the task. People produced a very comfortable level of force, constant, with 4 fingers, 5% of their maximum, so very easy. And then, at some point, they're asked, at the time of their choosing, to produce a pulse of force to a target. Very, very quick pulse. Okay? So they do that, and then a pulse of force. And there are 2 conditions. In one condition, they're doing it at any time they want. In the other condition, they're instructed to do it as quickly as possible to a beep that they hear. Okay? And then we compute the index of synergy. Well, when people synergy stabilizing total force by the 4 fingers. Now, usually the index of synergy is very high during constant force production because bad variability is very, very low, because people are very good at putting 2 lines on top of each other. But they vary the involvement of fingers from trial to trial, so good variability is not 0. And bad variability is pretty close to 0. So the index of synergy is very, very large. The question is what happens when they prepare to produce the pulse of force. So this picture shows a change in the index of synergy. So it starts from 0, but it's actually not 0, it's very highly positive. Now time here is shown in percent. This is not a typo because the data were time normalized by the time to the peak force during the pulse in each subject. So it's basically about 1.3 millisecond, 1%. So it's not exactly milliseconds, it's a little bit longer than that. You can see that the black line and the thin line show standard deviations. That the black line starts to go down, to deviate down, about 200 milliseconds or so before the pulse initiation. The forced pulse initiation was defined very conservatively, by the way, here. When the subject does the same task as quickly as possible to the signal in the earphones, so cannot predict when it will happen, then there are no changes in the index of synergy until the initiation of the pulse. So, an interesting result. People attenuate their synergies, make them weaker in preparation to a self-planned quick change in the variable. Makes sense, because if you try to change a variable that's strongly stabilized by your own synergy, you will be fighting your own synergy, because it will try to counteract your change in total force. So when we then studied it in different, okay, a picture for Professor Smilga. So this is from a study that we performed some time ago together, and it combined a physical model, which I described during the lunchtime to those who were there. The physical model is quite straightforward. Okay, you have a rusty bucket with a lot of holes. You start pouring water into that bucket. At some level of water, the pressure is such that the amount of water that flows in is equal to the amount of water that pours out. Okay? Then the system is in an equilibrium. Imagine that one hole becomes plugged by a piece of garbage, whatever. What will happen? The amount of water that goes down will become smaller. but the amount of water that's poured in is the same. The balance is violated, the level of water will increase, the pressure will increase, and the amount of water from other holes will increase too. Okay? So it will look like a synergy. You plug one elemental variable, you prevent it from changing, from contributing to the task, and other variables increase their contribution to the task. And a similar thing in the opposite direction will happen if one hole becomes larger, for example. So this is an illustration how this idea can be implemented in a kind of minimalistic neural network. So in this picture, it's for finger force production, because at that time we studied finger force production. So as a result, there are 4 elements and 4 neurons at that B level, big neurons that ultimately produce commands to individual fingers, well, finger modes. Then the output of these fingers goes also to small neurons at the C level that are shown there, interneurons, which are kind of like Renshaw cells that are very well known. So they project back, so we call it a back coupling, central back coupling model. They project back onto all the individual neurons with some kind of projections. Now, if all these projections are inhibitory, then this system will show you a very nice synergy stabilizing combined output of those neurons with any kind of noise that you add. However, if you change these projections, you can change it in such a way that the system starts to stabilize total moment of force. Total force or total moment of force, or both. So it's kind of a minimalistic example of a synergy that's based on very quick feedbacks from the output without waiting until the mechanical effects are produced back to the elements that are producing these effects. And it can be described with a matrix of projections. It's a 4x4 matrix because there are 4 small neurons and they project onto 4 large neurons. So time anticipatory synergy adjustments within this scheme are changes in the values of these metrics on the projections without changing the input into the system. So you plan to change the whole output of the system, but you prepare for that by changing the stability properties of that output or making it somewhat less stable. So this is a more schematic picture that when you have a task, you manipulate 2 types of neural variables. One of them defines average patterns of your elemental variables, and the other one defines correlation patterns of those elemental variables. So one of them will define what the system does, and the other one defines how stable it's going to be what the system does. And within this scheme, there are 2 changes, 2 types of preparation to action. One of them is anticipatory synergy adjustment, which is a change in this neural variable number 2 in correlation patterns. And the other one is anticipatory postural adjustment. And I put the FM for force and moment producing. Anticipatory postural adjustments produce changes in forces and moments. Anticipatory synergy adjustments produces none of those. You cannot see them. If you look at average performance, you can never see anticipatory synergy adjustment. You have to look at correlation patterns across trials to detect them. So this is, by the way, another picture of a very similar experiment with 4-finger force production, which we ran on older people. On top, there are younger people, and the results with these self-paced and reaction time trials are about the same as before. In the lower picture, you can see that older people have very small anticipatory synergy adjustments and very late ones. So they cannot prepare properly for a quick production of an action. This, by the way, is very similar to what is observed with anticipatory postural adjustment. So when you compare the two, you find out that there are some similarities. On the one hand, they occur, well, that's wrong slide. I mean, anticipatory postural adjustments occur 100-150 milliseconds. Anticipatory synergy adjustment a bit later, like 100 milliseconds later. But both are shifted in time towards action initiation when you ask people to do a simple reaction time to a sound signal, and both are decreased in elderly. So kind of too many coincidences, so we decided to explore the relations between the two. Okay. Here is the experiment because we decided to take a look at whether anticipatory synergy adjustments can be observed in postural tasks. Because until now it was only in multi-finger task, actually there is no posture, no postural component. So in this task we asked our subjects to stand and lean backwards a little bit. This was done on purpose because if a person stands quietly normally, the EMGs of most of the muscles are pretty close to zero, so you cannot record much. But we need to know synergy indices before the action. In order to make sure that these EMGs are not zero, we gave our subjects feedback on the location of the center of pressure and asked them to stand leaning backwards, and then do this type of movement. Okay? And again, the same type of analysis. We identified muscle modes. By the way, we identified them in 3 different ways because we were really worried about that experiment. We thought that it was, for us, it was very important, so we wanted to make sure that it's robust. We defined muscle modes using a different task and using the same task and with actually 2 different time intervals within the same task. And we defined the Jacobians in the same way. And this is the main result. So anticipatory synergy adjustments, one can very clearly see them. This is the index of the synergy. It's always positive in all cases. The 3 lines correspond to 3 different types of analysis. They are not exactly on top of each other, but the general pattern is very similar. They start with a highly positive value, and then about 200 milliseconds to 250 milliseconds before the movement initiation, the synergy stabilizing center of pressure start to drop and actually goes pretty close to zero. They all but disappear by the time the subjects perform the movement. It's also understandable because when people perform this movement, they expect a postural perturbation to happen. Anticipatory postural adjustments are never perfect. They never cancel out the perturbation. So the actual perturbation happens and it requires an adjustment, a very quick adjustment. Well, in order to do a quick adjustment, the variable to be adjusted has to be destabilized, and that's what we observe in this picture. And the same thing with the experiment that I showed you before with a pendulum hitting the person on the shoulders. Now, in this experiment, we asked our subjects not to lean backwards because otherwise, I mean, they would really fall. But we asked them to stand in a semi-crouched posture, so joints released. That made sure that there were non-zero activations of all the important postural muscles, and basically got the same result. This picture shows that, but there, to remind you, there were 2 phases: early postural adjustment and anticipatory postural adjustment. Prior to each of the phases, there was an anticipatory synergy adjustment. So it was a very complex time structure. So people changed their posture a little bit without realizing what they were doing about half a second before the pendulum hit them. And before that, they showed a drop in the synergy index, stabilizing their posture. And then a pause, and then anticipatory postural adjustment, 100 milliseconds before the hit, and again a drop in the synergy index. Okay. So this basically tells us about those studies, summarizing them, that there are 2 phases of postural preparation to action: early postural adjustment and anticipatory postural adjustment. The first one adjusts posture so that it optimizes its conditions for the planned action, and the second one generates net forces and moments counteracting the perturbation, and each phase starts with anticipatory synergy adjustment that attenuates synergies. Now, I showed this picture earlier during the discussion in the lab because now I want to link everything to a certain neurophysiology. So there is this thing that's called posture movement paradox. Look at these two body configurations, vertical and leaning forward a little bit.